Hi, this is EE637. I'm Charles Bowman, and today we're going to pick up on some of the material on entropy coding and the predictive coding, and then we're going to get into lossy coding. So, are there any questions, by the way? Friday's our last day, and then next week we have the exam, which I believe is on Wednesday, I think. Yeah. In the morning. Okay, good. So last time I was talking about predictive coding. Okay. Okay. So in predictive coding, the idea is that you try to predict the next bit from the sequence of previous bits, and then you do typically something like run length coding or Huffman coding, and followed by Huffman coding. And this would be a sort of a typical architecture that you would use for like coding binary images, for instance, in fax applications. And there is a number of standards that implement things that are of this flavor. CCITT Group 3 and 4, for instance, do that sort of thing. So a key piece of this is that you need to do the prediction of the you need to do the prediction of each bit from the previous samples, and so what you do is you just look at what the sample frequency is that's actually occurred in the actual training data you have. So you get some example images, binary images, say, and you want to code them. So you form a histogram where the histogram entries. This is just a fancy mathematical way of writing down a histogram. That's why I use the letter H here for histogram. So Hij at position S is equal to 1. If xs is equal to I and zs is equal to j, so z is so z is the previous pixels, and xs is the current pixel. So here we're just assuming that there's some states I and j. It's maybe easiest to think about this in the binary case. So here so you have so this is xs. X of s is equal to plus or minus 1, right? And so here you have 1, 2, 3, 4 values, right? So these are your 4 previous values. So you might have z here is like z sub s is going to be equal to, is a vector. It's 1, 2, 3, 4. 1, 2, 3, 4. So this might be x of S1 S2 minus 1, and then x of S1 minus 1 S2 plus 1, and x of S1 minus 1 S2, and then x of S1 minus 1 S2 minus 1. Okay? So that's pretty much it. So this whole thing here, z, these can take on binary values, each of these. So this is really a member of 0, 1. Oh, I have that as plus and minus 1. I guess I should put this as 0 and 1, say. And this would be like 0 and 1 to the 4. So it's a binary value, right? So it takes on values between 0 to, if you just put in decimal, 0 to 15, right? So you just have a table with 32 entries in it because you have xs and you have zs. So j here is a member of the set 0 to 15, and I is a member of the set 0, 1, right? And so the table is going to be of size 32. So here you have H is the histogram, and it includes the values 0 through 32. And now, so if you normalize that, it would be like a probability distribution or an estimate of the probability distribution on X, S, and ZS. But if you divide by the sum of this entry of this histogram over k equals 0 and 1, then you've normalized it so it looks like a conditional probability. So this becomes an estimate of the conditional probability of XS to given ZS. And then you can use that to predict. So you could say, well, I mean, in some cases it's useful to actually have this probability. For instance, if you implement an arithmetic coder, the arithmetic coder actually needs a prediction of the probability of each new bit so you can encode it optimally. We didn't talk about arithmetic coders, but arithmetic coders are entropy coders, but they don't have this problem of having an overhead of 1 bit per sample. So if you can tell it exactly the probability of each new bit, it can give you basically an optimal code. Optimal entropy code. So this could be useful, or if you just want to predict each new value and XOR it, then you can just check to see if this value is greater than, less than. You can check to see which of the two values, 0 or 1, is greater than the other, and then pick that value as your predicted value. So, okay, now. The other thing you can do is that you could actually adapt these codes. So you could have like a dynamic system where each new entry that comes in increments Hij to make it larger. And so the histogram just keeps adapting. And then, of course, you can adapt n. And then you just can calculate, n is the total number of counts you've observed. And in fact, you could even modify this with what's called a forgetting factor. And then you can have a predictor which is adaptive, so it adapts to the statistics of the data. And the thing that makes this all work is that if you design a coder, you have this causal predictor. This thing actually observes the incoming bit stream to calculate the histograms associated with the probability of each new entry given the past. And you'd say, so then that's used in this causal predictor, and then you can have this Huffman coding or run-length coding. You could also do arithmetic coding, in which the arithmetic coding would actually use the output of the causal predictor's prediction probability. So, but the thing that makes this all work is that you have a decoder, and the decoder can track exactly this, as long as no errors occur. If there's any errors that occur, then it can go bad. But as long as there's no errors that occurred, it can track it. So, assuming that, you Huffman decode it and you run-length decode it. So these are the exact inverses of this. So you get exactly this bit stream and that bit stream are precisely the same. Then what you say is, well, assume that XS is exactly the same as this XS. If it is, then this causal predictor and this adaptation process will use exactly the same input here and here. If it's a deterministic system, it'll produce exactly bit for bit the same output here. And if that output's exactly the same, well then this output's exactly the same as this. Well then the sum of the XORing of these two will exactly be the same as the XORing of these two, and that proves that this equals this. So as long as these processes are defined precisely, there can't be any noise or round-off error. The logic in all this has to be bit for bit the same, so that because if there's like one bit that's different, then the error will start building up between the decoder and the encoder, and they won't track. Okay, and in fact, those kinds of things you may have seen, like sometimes when you run, it doesn't seem to happen as much, but these days, but when you run a video decoder on your web page, and then you see the bits streaming through, and the video gets corrupted, and then it will start. It kind of gets worse and worse, and you have to reset the player. That's because there's a decoder. There's an encoder inside of the decoder. And if the two get out of track, they're supposed to be, the standards have set up, like for instance for MPEG encoding or H.263 or whatever, there's what they call iframes. So the iframes are sort of resets. So you do a, rather than, they're predictive coders in time, but every so often they'll just transmit the still frame in its full value. So in case the two sides get out of track because of missing packets in the network or various things that can go wrong, they'll come back in track. So this makes it kind of non-robust to any errors in the channel, but the channel's not supposed to have any errors, and you're supposed to use channel coding to ensure that. So, okay, so are there any questions about that? Okay, so the next topic that I want to talk about is lossy source coding. So, lossy source coding is based upon a concept of rate distortion theory, and we're going to talk about the Karhunen-Loew decorrelating transform, and a little bit about practical coder transforms. And you're going to implement, well, for this final lab, you're doing a JPEG coder, which is kind of a nice thing because you have to implement a Huffman coder, okay? And then, so that gives you about a sense of how an entropy coder works. And then you have to, but then you have to actually do lossy coding by doing a transform and quantization. So the way in which a coder works is you have an incoming stream X, okay? And then, I think I drew this before. The first thing you do is typically you do a transform of some kind. So the transform can be like a DCT, or it can be a wavelet transform or whatever, right? And then the next thing you do is quantization. Okay, and the quantization is where the actual loss occurs. If you didn't do quantization, at least in theory, the transform would be invertible typically. Often this is an orthonormal transform. If it's not orthonormal, it's close to orthonormal. And then you do entropy coding here. And this is the coded output Y. And then to decode, you reverse this. And there's two basic kinds of transforms that people use here. Well, I mean, there's lots of different transforms, but you'll often hear about block coding. And examples of this would be like the DCT. You're going to use the DCT in JPEG coding, that's block coding. So block coding is nice because you operate on blocks of the image at a time, and you don't have as many problems associated with it's more local when you do the computation. So for instance, it's very easy to get, if you design an ASIC or just about any kind of hardware, like what do they call it? An FPGA. You can get blocks that are pre-designed for you for JPEG coding because you just plop them in. They've already been debugged and designed and optimized. So it's very simple because it only operates on an 8x8 block. So there's not a lot of memory. There's only 64 values that it has to buffer. It does have to buffer 8 lines of the image. And most image processing algorithms tend to be line-based, so that's extra memory buffers, but it's not too bad. Then the other thing, so there's wavelet transform. So wavelet transform would be like JPEG 2000, which isn't very widely used. JPEG 2000 is actually a suite of different standards. But the thing that people most associate with it, and the sort of the baseline coder that's the core of what the standard is based on wavelets. And they still try to do the wavelets in some block-based methods. But wavelets are intrinsically not really a block-based transform. So the problem with wavelet-based transforms is that, well, they have some advantages in that there's some redundancy in the DCTs. Basically, you don't capture a lot of the redundancy that occurs across block boundaries. So there's more advanced techniques that have been developed to handle that. But if you don't do anything otherwise, you tend to get blocking artifacts, and you'll lose coding efficiency along the blocks. And if it's an 8x8 block, that's not so big, so that's pretty significant, right? I mean, the boundary is 32 pixels, right? So it's almost half the pixels are on the boundary of the block. So you can't ignore the block boundary. It's not insignificant. That's probably where most of the loss in JPEG. I should put here JPEG and the DCT. Oh, I have this backwards. I should have put, okay, so, and then, so that's important. But there's more advanced methods. Actually, there's a new method that I think is going to actually catch hold, but we'll see. It's the Microsoft has a standard for image coding, which is something like, does anybody know what this is? If nobody knows what it is, that's a bad sign.
SVG.
Huh?
SVG?
No, it's called high def image, or nobody's heard of this? Oh, not a good sign, huh? Scratch that. Maybe it's not going to take hold. Okay. But it's a sort of an updated JPEG that is supposed to address the major problems with JPEG. This is the part of the lecture where I'm just sort of talking about like the state of the art, okay, as opposed to a lot of technical detail. But so the problem with let me write this down. This is kind of useful information. JPEG, in case you're using JPEG a lot, okay? So the problem with the good thing about JPEG is it's simple and memory efficient. That's probably its biggest advantage because it just uses this little block. It's very local memory access. So it's very easy to implement in hardware. Okay? The bad, okay, is that its compression efficiency is not so great. Compression efficiency is maybe, I'm just really pulling this out of the top of my head, but I'm sort of thinking maybe 20-25% higher than the current state of the art. So you lose about 25%, something on that order. But the other thing is it breaks down at low bit rates. And so it's sort of in its sweet spot where it's designed for. It's not too bad. It might be within 15% of a reasonable okay coder, and maybe 20% of the state of the art. But at low bit rates it behaves poorly, and it tends to produce blocking and contouring artifacts, which I'm sure you've all seen in JPEGs. Okay, so that's JPEG. The wavelet-based methods. Oh, and the other problem is, this is the good, the bad. Oh gosh, I have the extra category, the ugly. 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 How do you spell ugly? Is that correct? Okay. The ugly is that when they created JPEG, they were really, they did a fantastic job, okay? They really hit it out of the park, okay, with JPEG. I mean, you got to give them credit. Because this was made in, like, 86 and 87. So they were looking ahead pretty far. That was pretty good. But they screwed up on some things, okay? So one thing is there's no real color space. People routinely use YUV, whatever that is. I guess it's open to a controversy what YUV even is. Okay, but whatever YUV is, they think that they use that in JPEG, but it was never codified as the standard. And the other problem is it's only 8-bit color, right? So 8-bit color is a problem because, what's the problem with positive? Unsigned. So what's the problem with unsigned 8-bit color? Hey, that would be a great test question, by the way. Unsigned 8-bit color. What's the problem?
No negative.
No negatives. And what does that mean? I feel like I've been pounding this into everybody's heads for like at least a month and a half. What happens if you don't have any negatives? Come on, guys. Make me proud.
Too late.
Oh, I know you have it in you. I know you can do it. Come on, work with me. Someone take a guess. What happens if you can't have negatives?
To me, it's all zeros and ones. So.
You can't produce colors, right? You have a limited gamut.
It's all zeros and ones, though.
Actually, I'm kind of lying a little here because it is YCRCB or something like that. So you have, but even then, the color transforms, I think, assume that you have RGB input. So usually it's clipped to positive values of RGB with whatever color format you have. But JPEG has a limited gamut, okay, color gamut. So, and guess what one of the most important uses, commercial uses of JPEG is? Name some important commercial uses of JPEG.
The internet.
There's a biggie, okay? That's probably the biggest, okay? But internet, you could, if people wanted to use other kinds of standards for images, that wouldn't be too bad because, let's see the bad here. The compression efficiency, well, you don't care that much about that on the internet, right? It's just images. Breaks down at low bit rates, that you don't care too much about. Blocking and contouring, that's kind of a pain with text and things like that. But its advantages are that it's simple and memory efficient and local memory access. These aren't very big advantages on the internet because you're just doing this on a general purpose computer, right? So you don't really care about that much about memory efficiency. You have at least, a modern computer, even a not so good modern computer has a megabyte of RAM in it, right? So it's not that big a deal, okay? But what's the second most important application of JPEG? So you could go to something else that was less memory efficient, like wavelet coders.
Talking like digital photography or something?
Digital photography, digital cameras. That's huge because that's a real driver for the technology, right? I mean, if they have a good format, then people buy more digital cameras. So it's basically that's a driver for the camera market, the digital camera market. So here, color is very important in digital photography, right? So that's a real serious disadvantage of JPEG. And most the high-end digital cameras will support other formats, but what mostly people use is still JPEG. So that's a problem. So Microsoft and I think HP maybe came out with a standard whose name I can't remember. That's also a block-based coding standard, which is basically reminiscent of JPEG. But JPEG 2000 was wavelets based. JPEG 2000 never really caught on. And the reason is so the good is better coding efficiency than JPEG. I'm not sure they ever took care of the color issues. Okay, I won't put anything down here because I don't want to malign JPEG 2000 unless I'm sure. But I don't know if they ever really took care of the color issues. I'm pretty sure that in the new Microsoft standard they did. And but the bad is that and no blocking artifacts. But the bad is that memory in a wavelet transform, it's like a tree structure. The wavelet transform, the simplest wavelet transform is like a Haar transform. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you subtract two coefficients. You take their difference and their sum. This would be the simplest wavelet transform. You take the difference and the sum, all right? The difference is sometimes called the detail coefficient, and that represents the local variation in the image. Okay, in 2 dimensions, this would be over a 2x2 block. So you take the difference between every 2 pixels. If you take 2 pixels that are adjacent to each other, you take their difference. Is the difference going to be? Tell me something about the difference.
It's going to be positive.
No, the sum will be positive, right?
Oh, so we're not assuming any kind of order?
If you take the difference between 2 neighboring pixels, right, they'll generally not be positive, okay? It'll be positive or negative, right? Mm-hmm. And will be small or large?
Small.
Just intuitive. It'll be small, right? Because nearby pixels tend to be similar. If you take the sum, is it going to be small or large, positive or what? Sum's going to be positive and tend to be large. Mm-hmm. So the difference codes well, and the sum doesn't code as well, right? That's like the low frequencies and the high frequencies. So you take like that.
What transform?
This is a Haar wavelet transform. So people don't use Haar transforms for really coding images, but it's the simplest transform to actually understand. It's very simple. It's what you might do without actually, this is just a fairly ad hoc thing to do that you might just, without knowing what you're doing, just guess at it, right? Take pairs of pixels that are adjacent, subtract them, quantize and code the difference, and then repeat, okay? Pretty simple, right? Yeah. So now you're very sophisticated because this is a Haar wavelet basis, okay? Now, it turns out there's a whole theory of these kinds of transforms. This has the property that it's orthonormal, and it's an orthonormal transform. So the number of pixels in is 16. The number of entries you have to code out is also 16. So you haven't created any extra data, so that's good. And there's a whole theory of other transforms, of orthonormal wavelet basis transforms. It turns out that among all those transforms, the Haar basis wavelet is unique, and that it's the only transform where these individual coefficients are computed by the averages, which is a symmetric kernel. So what ends up happening is that the kernel, that if it's an orthonormal basis, tends to be asymmetric, which isn't good because the asymmetry is unnatural. But there's so there's some glitches. The theory's not a perfect solution to everything, but Yeah, this is, at least now you know, roughly speaking, what a wavelet transform is, okay? Yeah.
Is it similar to DFT?
Yes and no. I would say it's related, but I wouldn't say it's similar. Because the DFT, DFT actually has global communication, right? So it's, okay, this is a tree, and a DFT is a graph. If you look at the implementation of a DFT, it kind of looks like, I mean, you probably know what a DFT looks like. Do you know what it looks like? Okay. Well, I mean, it looks like this, right? 1, 2, 3, 4, 5, 6, 7, 8, right? You take a butterfly.
Yeah.
Okay, so first of all, that's not a tree, okay? Now, that first butterfly actually looks exactly like the Haar basis because you actually, it turns out you take a sum and a difference. So in that sense, it's very similar. But then it continues on, and I can't draw this. I mean, it's something like, then you take a butterfly between these two and between these two, I think is the way it works, okay? And then you take it between these two and these two, okay? All right? And then what happens is you take it between these and these and these and these. Okay? So, this is a fast transform because it's sparse. This is an FFT.
Right.
And the DCT there's a similar kind of implementation. And in general, if this was X and this is Y, right, then you have Y equals AX, that this is an n by n matrix. So how many multiplies does it take to multiply an n-point vector by an n by n matrix? It takes n squared, right? Yeah. But how many multiplies does it take to do this? Well, it turns out the number of butterflies you have to implement is basically n log n, okay? So it's sort of like a tree because it's like a binary tree, also has log n steps, but this complexity is n log n, and this complexity is n. There's no log n. Because, and this is a little bit surprising, because the number of levels of the tree is log n, but the total number, I mean, how many, anybody who studied graphs, right? How many internal nodes are there in a balanced binary tree with n leaves?
-1.
N minus 1, right? So the total number of operations that has to occur here is just proportional to n.
Right.
So this is linear in n, and this is n log n.
Right.
So this has higher complexity. But they're kind of related. They're both orthonormal transforms. They're both sparse because they don't have n squared operations, right? And there's been a lot of interest. There were a lot of interest in wavelets for a long time because the idea is that you can get both localization in frequency and time. So if you have like a sharp edge here, the sharp edge will propagate up, but not so badly, okay? Whereas if you have a sharp edge here, it sort of splatters all over the frequencies, okay? So you get more localization in a wavelet transform. And if you did a DCT over the whole image, that'd be horrible, okay? Because you have the DCT of the whole image is huge. A wavelet transform of the whole image is typically the kind of thing they're talking about. So the problem is that you have a lot of communication going on. It's a fairly complex process. And if you did a wavelet transform on an 8x8 block, well, that wouldn't be big enough. So then you lose a lot of coding efficiency. So the bad thing about wavelet transforms is that they're harder to implement. You tend to need larger buffers. Yeah. So this is just a little bit of my biased view of the world. Okay. Okay. Now, Carhoon Labs. Well, I'm going to talk about that later. Okay. So now. Okay. So we're going to talk about rate distortion. Rate distortion. So the idea in rate distortion theory is that at a particular level of distortion, you have a certain minimum bit rate that's required to communicate the signal. And it turns out that if you can get arbitrarily close to that. So I'm going to introduce, in a somewhat flawed way, this underlying theory. If you want to really learn about this in more depth, take information theory, which is ECE 642, okay? So, so the distortion between X and Z is let's say we're using a squared error distortion metric. So we take the norm of the difference between X and Z, okay? And if they're both random variables, so, okay, I didn't even say what X and Z are, but hold on for a second. Okay, and then, so if why is there, okay, okay, this is a little unclear. Okay, so the expected value of this is the expected distortion. Now, you say, well, what's Z and Y and X? Okay, okay, the idea is this. X is the thing that we want, okay? So X is, what we do is we have like X, okay? That's an image, for instance. Say image. Okay? And then we put this in the coder. Okay? And the coder produces Y. Y is a binary bit stream. Okay? And then, okay, then what we do is we decode. And the decode here is Z. Okay? So the distortion then is X. So if I want to compute the distortion between X and Y, so Z is a function of Y. If I know Y, I know Z. So I want to say for a particular Y, what distortion will I get? Okay? So the answer is that the distortion of XY is going to be, or the expected distortion, so I guess I can call that uppercase D, is the expected value of I take the norm of X minus Z squared. Okay? So that's the expected distortion. And it's going to be a function of the bit stream. And of course, it's going to be a function of the coder and decoder I use. But the beauty of this theory, and it is a little bit of a bizarre theory, okay? It's not the sort of thing you might come up off. I mean, it's not obvious, okay? Which is why Shannon was a smart guy. But is that you don't say anything specifically about there being a thing called a coder and a decoder here, okay? It's done all independently of that. So what you do is you say, okay, you got an X, and Z is a coded, Z is the decoded image, and then Y is the coded image, okay? And, okay, so fine. And, okay, this just points out that the thing, you could reformulate everything with not mean square error, because I've spent a lot of time saying that mean square error isn't very good. So you can use any other norm. So you can use any positive definite matrix B here and look at any squared error, okay? So, so what happens then is, okay, so now, okay, the notation is going to get a little messy. So now what happens, and you're going to wonder, well, why do I need this, okay? But instead of just having one X, we're going to have a series of X's, and we're going to have M of them, okay? So, each X is a new, so we're going to have a series of independent observations. So instead of it being like one image, we're going to have a series of independent images, each of which is a random object. Okay, and the reason it turns out we need that is that all these results are going to be asymptotic. So it's not really true for just one. We have to have an infinite number of them for it to become true. In practice, it's close for one, okay? So Y is the encoded version of all the X's. So what ends up happening is that we use K bits, okay? So somehow you encode it with K bits, okay? And then Z is the decoded version, okay? So then what happens, so the encoder I represent as Q. So I take the entire sequence of images. Now, or these could be actually, let's just think of these as scalar values. And they are independent scalar values. You'd say, well, why are we coding independent scalar values together? This is the mysterious and miraculous thing that happens with source coding, that it's better to code independent values together than apart, even though they have nothing to do with each other. And just to give you a little bit of quick intuition into that, because we haven't talked about this, is that, okay, so actually, you know who knows about this result? Honeybees. Okay? Honeybees know that this is true. Okay? Why? Because when honeybees want to store honey, how do they do it? They make a what?
Packed into honeycomb?
They pack it into a honeycomb. And what do honeycombs look like? Is this what honeycombs look like?
No. Hexagon.
No, honeycombs don't look like that, right? How do honeycombs look? They look like this. Oh God, I'm really bad at this. Right? They're hexagons, regular hexagons. So why are they regular hexagons?
Nature says.
Because regular hexagons optimally pack. Well, I'm not sure that this has ever been proved. It might actually be still an open conjecture, but everybody knows that it's true. That hexagons optimally pack the 2D plane in the following sense. You can ask the question, okay, for a certain amount of honey, wax, okay, which is waste, okay, that you want to maximize the amount of honey you store, okay? So this is more efficient, okay? Another way of looking at it is this, that if you're doing a thing called vector quantization, okay? So if you had x, so x is equal to x1 comma x2, and these are independent random variables. They have nothing to do with each other. It's better to code them together than apart. Isn't that really a ridiculous result? But it's true. Because what happens is this. Let's say this is uniformly distributed, okay? So let's say they're uniformly distributed on some very large intervals. So locally it looks uniform. What's going to happen is this. If you look at the mean square error in each cell, okay, it's going to be a function of the distance of, right? So, and then, for a particular, if you fix the number of cells and you want to minimize the mean square error, this is optimal. The optimal 2D structure in terms of minimizing the mean square error for a given volume is a sphere, right, or a circle in 2D. But that's why bubbles form spheres. Okay, but the problem is spheres don't pack well. So they pack optimally if you put them in honeycombs like this. So you actually can pack. This gives you better quantization efficiency. So there's this unintuitive result that it's better to code things that are independent together. You get a little better efficiency. So the theory has to account for that, and that's why we have to have a sequence of x's which are independent, because otherwise you can't achieve the bound. So, because otherwise you're losing efficiency. So then what happens is you have a quantizer that quantizes. This is actually a vector quantizer now, because it's going to quantize the vector of x's as opposed to the scalar values. And then f here is the decoder that takes y and produces the z's, and then you can look at what the distortion is. Okay, so now I've already introduced this other concept, which is differential entropy. Differential entropy is just like it's completely different than regular entropy. Okay, it's not just like regular. It has a mathematical form very similar. You replace the sum with the integral, but for a continuous random variable, what's the entropy if x is a Gaussian random variable with mean 0 and variance 1, what's the entropy of x? How many bits does it take to code x? Infinity. Because there's, there's an infinite amount of information in the variation. Any generally continuous random variables are going to have infinite entropy, but their differential entropy is not infinite. That's well defined, okay? And the use in all that is that you can define conditional entropy and mutual information appropriately, even for continuous random variables. So entropy is only well defined for discrete random variables, but conditional entropy and mutual information is well defined for continuous random variables. So you define the conditional differential entropy and the conditional entropy. You subtract them, and that gives you the mutual information. Okay. So, and it turns out you can prove that the mutual information is a symmetric function. So the mutual information between x and y tells you how much information in units of bits, if it's bits if this is a log base 2. It tells you how much information in units of bits are between x and y. So, yeah, that's kind of interesting. Okay, now, the rate. Okay, so we're going to define a concept of rate. This is not very intuitive, but before I explain what the concept of rate is, because it's not very intuitive, rate represents the number of bits per sample it takes to encode something, okay? But now I'm going to give you the true definition, and it's going to seem crazy, okay? So you take z, the decoded quantity, and you take x, okay, and you take them, so this is like, this is x for just one sample of x. And you take the mutual information between them, right? And you say, okay, the mutual information between z and x is how many bits it would take to be able to encode x to get z. See, if the mutual, intuitively, I don't have a proof of that yet, but this is where we're going, okay? That this mutual information it tells you how many bits are in the decoded image when compared to the uncoded image, right? Now what you do is you say, okay, I'm going to look at all possible encodings of the image, and I'll look at all possible encodings such that the distortion is less than some delta, where this is a lowercase delta. And among all those, I'll pick the one with the smallest number of mutual information. So I'll look for the encoding of x with the least amount of mutual information that meets some constraint on distortion. Obviously, if I allowed any amount of mutual information, then I could achieve a distortion of 0, because I could make z just equal to x. Then the mutual information would go towards infinity, and the distortion would go towards 0. If I allow any amount of distortion, I can make z just a constant, 0, right? And if z is a constant 0, well, then there'll be some distortion. It'll just be the mean square or an x. And, there'll be unconstrained, but then the amount of mutual information will be 0, because they'll be independent. If two random variables are independent, their mutual information is 0. So now, and it turns out that you can show that this function, so for a particular delta, this gives you the rate, the minimum rate associated with a particular delta, which is a distortion. So this is the rate distortion function. And you can show this is a convex function, which is interesting. And then the important theorem that ties this all together is Shannon's source coding theorem, which says that if you pick any rate above the theoretical rate, and you pick any distortion above the specified distortion, then you can find a coder, okay, for some n, but n may become very large. N is the block size. You can find a coder such that k is the number of bits in the encoding, n is the number of samples you encoded, n. So k over n is less than r prime, and the distortion is less than d prime. So in other words, if you give me any rate and any distortion such that the rate is above the minimum rate and the distortion is above the minimum distortion, then I can find a coder that will achieve that rate and distortion. But the caveat is that the block size can go towards infinity. The block size can grow rapidly. And that has some practical implications because a large block size may not be practical. Okay, so the proof for this doesn't lead to a practical coder, but it gives you a lot of insight into the fundamental problem. So we'll finish this up on Wednesday, and then maybe on Friday we'll do some review if that's what people would prefer to do. All right, good. Thank you very much.